Hello everyone, my name is Zain and I'm a student at the University of Picardie Jules Verne, France. The topic of presentation is multiple model and observer design for a water-based PVT collector. The presentation is divided in the following sections: Introduction, Modeling, Multiple Model, Observer Design, Results and Discussion, and presentation ends with conclusions and perspectives. Solar energy harvesting is becoming popular because of global warming, rise in fuel prices. Renewable energy has been one of the main areas of interest by governments of nearly all countries. Solar energy is clean and the most abundant energy source available around the globe. A PVT system combines photovoltaic module and thermal module into one integrated unit. Heat is produced by the thermal module, whereas electricity is generated simultaneously by the PV module. The total efficiency is more than 50%. The circulation of fluid plays a crucial role in heat extraction, and this fluid can be air, water, phase change material, or some nanofluid. It not only produces heat but also reduces cell temperature, which results in an increase in PV efficiency. These systems have various potential applications such as drying, cooling, heating, etc. The advantages includes these systems are less bulky, simple to operate, the mediums found abundantly, these systems work in all temperatures, they have no corrosion issues.
Various studies have been conducted and a variety of different design configurations of PVT collectors such as air-based, water-based, glazed, unglazed, PVT with natural or forced circulation flow are addressed. In this work, water-based PVT collector is considered. It is the most common domestically used panel and produces more energy than individual conventional PV and solar thermal panels installed over same area. Cold water is injected from one end of the panel and warm water is collected from other end of the collector along with electrical gain. The collector is composed of several layers: glass cover, PV cell layer, Tedlar layer, an absorber plate, parallel water tubes, fluid which is water flows within these tubes, an insulator to reduce heat losses while improving structural strength. Few assumptions have been made for the thermal model. The losses at the edges, pressure losses, partial shading, and dust are oversighted.
Here we give a dynamic thermal model of a PVT collector using energy balance principle for each component and layer of a collector. The dynamic energy balance takes into account masses and heat capacities of each layer to derive temperature of each component by considering radiative, convective, and conductive thermal exchanges between the layers. Here Tg is glass temperature, cell temperature, Tedlar temperature, absorber temperature, metallic tube temperature, fluid temperature, and insulator temperature, where Ep is the fraction of absorbed solar radiation that is converted into electricity, and Tw is the arithmetic mean of inlet and outlet temperatures. The thermal model then can be expressed in state space form, where state X contains the state variables, output Y is the water outlet temperature, mass flow is defined as control input, V contains the disturbances, solar radiation, ambient temperature, and water inlet temperature. There are several methods that can be used to procure multiple model, which includes identification, linearization, and mathematical transformation. In order to simplify B of x for thermal model, we make change of variable, which will allow us later to design observer. A new state theta W is introduced, which is a difference between average fluid temperature and inlet temperature. The proposed multiple model is based on convex polytropic transformation of nonlinear functions that uses boundedness of nonlinear terms. The thermal model with change of variable is expressed as this, where a new state vector becomes this, where we have a new variable theta W. In the thermal model, the varying term is h of I sun, where this is the minimum of solar radiation and this is the maximum of solar radiation, which enables us to obtain mu1 and mu2. The number of models depend on number of nonlinear terms, and two possible local models available described by A1 and A2. And the corresponding multiple model can be written as this. It should be noted that radiative heat coefficient is not varying much, so taken as constant by taking the mean of all the values. Designing observers for nonlinear system is a challenging problem due to its importance in automatic control design such as control, monitoring, and fault diagnosis. An observer is designed for estimating the states of the system, and linear matrix inequality is used to compute the observer gain. First, let us notice that B bar of X bar can be written as this one, where an observer of the corresponding multiple model is expressed here. MATLAB program is used for the proposed observer. Initially, the simulations are performed to see the response of the nonlinear model and its corresponding multiple model. The obtained results indicate a good representation of the nonlinear system. The simulations are performed by randomly choosing system's initial conditions and observer initial conditions. The system real states presented in Figure 4 are tracked by the observer states presented in Figure 5. Figure 6 illustrates that the estimation error converges to 0 for all of the states, thus displaying the effectiveness of proposed scheme. The estimation error converges to 0 even if the initial conditions for the observers are changed. Here the parameter gamma can help us in this case. Heat transfer using water as a working fluid is high compared to air. It is obvious that the temperature of the PV component is higher than the other components. Realistic disturbances can be included to examine the stability and accuracy of the observer. There is a need for physical experimentation to get better knowledge of its feasibility and efficiency in real conditions. The practical experimentation will be done around equilibrium points, and these points will be changed for validation. The authors would like to thank European Solarize Project for the support.
Thank you for your attention.